Okay, in this video we're going to talk about some other things that can change the equilibrium position of a reaction. In the earlier video we talked about like what would happen if you either added or removed products or reactants. In this video we're going to talk about first about like what would happen if you changed the temperature. All right, another way of saying this is what would happen if we heated or cooled the reaction. All right, so the way that you're going to go about this is first of all you want to identify your reaction as being either exothermic or endothermic. All right, remember exothermic is when it releases heat, endothermic is when the reaction absorbs heat. And then one way that helps is if you write the reaction where you show heat as being either a reactant or a product. All right, so let's for example use this particular reaction right here, and we know that the delta H, which is the change in enthalpy, is 87.9. All right, notice the way that's written, that's a positive number. And when that's positive, that means that it's endothermic. All right, and remember the reason we could, if you want to, recall why is this considered endothermic? Why is this thing considered to be something where it would be absorbing heat? All right, well, remember that delta H means the change in enthalpy. All right, so the change is always the change, what you have at the end minus what you have at the beginning. So in order to have a positive change, you have to have more energy in the end materials than you do at the beginning. All right, so if you just, what this would mean is that these combined right here have a higher amount of energy than what you had the material did at the beginning. All right, so how does it get that energy? The energy just can't come from nowhere. It had to come from heat that got put into the material. All right, so that again is why positive changes in enthalpy indicate endothermic reactions, whereas negative ones are exothermic. All right, so since we know that heat has to be put into this reaction, we could draw that as a product. All right, sorry, not as a product, but as a reactant. All right, so the PCl5 plus that heat is going to give you the PCl3 plus the chlorine. All right, so one way to think about the way the temperature would affect this is just to think, all right, well, if I lower the temperature, that's essentially the same thing as taking heat away. All right, I would be pulling some of that heat away from this reaction. So just like in the earlier examples of adding or removing products, if I remove something from over here, that's going to shift this thing to want to go to the left. All right, if I add something to a side, it's going to want to shift things away from that side. So if I lower the temperature, I'm taking heat away, it's going to shift to the left. But if I increase the temperature, if I bring this guy up, it's going to shift this to the right. All right, so the opposite would happen for exothermic reactions as compared to endothermic reactions. And just a quick review, some ways that you could spot endothermic reactions. Either if you have an energy diagram, endothermic is going to be higher at the end than at the beginning. It's also going to show, you could also see a reaction where it shows heat as on the reactant side. Also, it's going to be something that's got a positive delta H. All right. By contrast, things that are exothermic have lower products than reactants. They show heat as being a product rather than a reactant, and they also have a negative delta H. All right, so whenever you run into a question where it says how would the reaction respond if it was heated or cooled, this is going to be the first question you need to answer: exothermic or endothermic. Okay, so one common topic when talking about how things affect equilibrium is what would happen if you change the pressure in a reaction. All right, and this is actually a fairly complicated topic because there's more than one way to change the pressure. All right, one thing I'm going to say is that whenever they talk in a lot of problems about like what would happen if you change the pressure, generally they're talking about this first situation right here. All right, where you're changing the pressure by either compressing it or expanding something. All right, but I want to point out that that's not the only way you can change the pressure. All right, so there's not, if you're going to be precise about this, if you said how does changing the pressure of a reaction affect the equilibrium, you'd have to first ask the question, how are you changing the pressure? All right, so we're going to go through 4 different ways that you can change the pressure. and see how, depending on the ways, it would have different effects. All right. So the first one is going to be the most common, which is either compressing or expanding a gas. All right. So let's say we had our reaction where, again, we'll just say A plus B can yield C. And we've got all these things in a syringe, and this has got a movable partition. So this would be like a syringe, and we can compress this, and essentially you're just going to move this to the right, and it's going to squeeze these things into a smaller amount of space. All right. Well, I think we all know that, when you do that, it's going to be the material is going to be at a higher pressure after it's squeezed into the smaller space than before. This is classic Boyle's law, which I'm not sure whether they refer to it as Boyle's law in sophomore chemistry, but the equation is P1V1 equals P2V2. The question is, how is this going to affect a reaction that's at equilibrium? All right. Well, the thing to remember about this is when you compress these particles into a smaller amount of space, compressing has the effect of essentially increasing the concentration of the gas particles. All right. Just take these two situations. You have the same number of particles in both of these. It's just that these particles are in a smaller amount of space. All right. Therefore, the concentration of the particles has got to be higher over here. All right. So here's an example of how this would work. All right. Let's pretend that we have this reaction right here. All right. N2O4 is in equilibrium with 2 NO2s. All right. So at equilibrium, I'm just going to go and say, here are your concentrations. All right. So if those are our concentrations, well, I could take a look at this reaction right here, and I could write an equilibrium expression, and I could take these values and I could plug them in to where they would go into this equation right here, and I could calculate that the KEQ would be 8. All right, for this particular reaction, the KEQ would not be 8, but I'm just using some simple numbers to demonstrate a point. All right, so I do want to point out that we're just going to make the assumption that this is in a 1 liter. This is in a 1 liter container. What we're going to do is we're going to assume that we take this reaction, which is at equilibrium in a 1 liter container, and we're going to compress it to half the volume. We're going to compress it to 0.5 liters. All right, essentially, you can think of it as it was 1 liter, and we're going to move this wall so that it's halfway here. All right. So how's this going to affect things? Well, what it's going to do is it's going to essentially change the concentration of these things. And a way that you can see how it would originally change the concentration is just to apply M1V1 equals M2V2. All right. We have an original molarity. So even though this equation is usually used for solutions like diluting or concentrating a solution, it can also be used for either compressing or expanding a gas. All right, because essentially you're just changing the concentration of the particles. All right, so we have an original molarity, an original volume. Let's find out what our new molarity would be at its new volume. All right, and you can see that the molarity ends up going up. All right, and hopefully that would make sense. If you squeeze things into a smaller space, the concentration should go up. All right, so that's our new molarity for this material. We can do the same thing for the other material. This would be its new molarity. And remember, this is KEQ when it's at equilibrium. All right, but we also have this other value Q, which is what things are at the present moment. All right, so we could take, so the moment after you compress this, we could take these values right here, and we could plug them back into the equation, and we can see that this is our new Q value. All right, and if you're wondering, why does the Q change? All right, well, the reason that it changes is because the top value was squared and the bottom value was not squared. All right, and so when you changed these molarities, it had a greater effect on the part of it that was squared than the part of it that was not squared. All right, so notice that 16 does not equal your KEQ because we figured out earlier that our KEQ was 8. All right, so in fact, we could also say that the numerator here is too high. All right, in order for this Q value to become this, we need for this numerator value to get smaller. We need for this denominator value to get larger. All right, so ask yourself, if we need this stuff right here to get smaller and this stuff right here to get greater, essentially what that's going to involve is some of these things right here reacting to make some of these things right here. And that involves by the reaction, the reverse rate increasing. All right, so this can be accomplished if some of the NO2, which is this stuff right here, goes to the left, and that makes some of this. All right, in doing that, you're going to reduce the amount of this, so you're eventually going to start getting a smaller numerator. That's going to increase the amount of this. That's going to increase the size of your denominator, and that's going to move this towards restoring the equilibrium, and it's going to happen until that happens. And that's going to happen when your Q, which is what your current concentrations are, equals your KEQ. All right. Another way you can change, so that's the most common way that pressure can change. But another way that pressure can change is just by heating something, all right, where the volume is fixed. All right, so if we just take a gas in a metal box and you heat it up, all right, so the pressure is going to increase here. All right, and hopefully you remember that if you heat a sample of gas at a constant volume, the pressure is going to increase, and it increases because when you heat this up, you're going to have more frequent collisions of your gas particles, and the collisions are going to be more forceful. So that's going to result in an increased pressure. All right. Well, the thing about this is, unlike the previous problem where the concentrations would change when you compress things, here the volume's still the same and the number of particles in that volume are still the same. So the concentrations aren't really changing. What has changed is that the temperature is going to change. All right. And so when the temperature changes, so one thing I failed to mention earlier is that the equilibrium constant is specific to a given temperature. All right, and that's because the rate constants, the forward and the reverse rate constants, are given for specific temperatures. All right, so the equilibrium constant at T1 is not equal to the equilibrium constant at T2. So essentially, this is just something where you treat this as just a heating problem. All right, compare what your current concentrations are Q to the new KEQ at your new temperature, and see which way the reaction would have to go in order to restore the equilibrium. All right, and we'll practice some examples like that. All right, another example would be if you were to add particles or products. All right, so let's say again we get this reaction, we got these materials in a box, and we're just going to pump some NO2 into O2. Like, let's say that this is like a bicycle pump, and we can just pump some of these molecules into this box right here. All right. Well, if these were the original concentrations, and this is 1 liter, and we pump 1 mole of this stuff right here in there, well, our new concentration of that would be 3 molar. All right. And if you calculate the Q for that particular reaction, notice it's not going to equal your KEQ. And you're just going to have to figure out which way this reaction would have to go. Well, if we increase the amount of this right here, well, that means that some of that's going, there's going to be too much of this, and it's going to have to, some of this is going to react to create some of this, and that's going to act to restore the equilibrium. All right. Notice that if you add either reactants or products, it could shift it either way depending on how it affects the Q. All right, and you just have to plug the numbers in and see which way things would work. All right, but one rule of thumb is if you add something that's on one side, it's going to shift it to the other side. So if I add some of the products over here, it's going to want to shift it towards the reactants. All right, so the last and probably the least obvious of the ways that you could increase the pressure is by adding an inert gas. All right, so let's pretend that we've got our reaction mixtures here in a 1 liter box, and instead of adding the previous example where we added either some of the reactant or the product, well, let's say that we pumped in just some helium gas. All right, well, helium is not going to interfere with this reaction. It's not going to react with anything, and so in your new stuff, in your new situation, your concentrations haven't changed. All right, there's still the same number of moles in the same volume. Those are the same. You just have this this other gas that's around that doesn't change anything. All right, so the reaction would still be at equilibrium and no change would occur.